Here is Cyrill Muratov from the University of Pisa, and he is going to give an overview of Skyrmions and ultrathin magnetic fields.
Well, thank you very much for the organizers to give me an opportunity to talk about this work, this joint work with Anberna Montel, Giovanni Di Fratta, Antonio Montel, Teresa Simon, and Valery Slastikov, and oops, sorry. So, as you know, Anne is here, Giovanni is here too, and Teresa is the chair, and Valery is somewhere in the clouds. Okay, and I have to also express some gratitude for the Newton's Institute, because the early stages of this work actually happened in this very building with I guess 4 of us, of how many? Me and Anne and Giovanni and Teresa and Slastikov discussing this in the spring semester program here at the Institute, which we are sort of following up in our today's meeting. So this actually works. Okay, so briefly, this work has enjoyed support from the National Science Foundation when I was still at the United States, and it's continuing to be funded now by the Italian Ministry of Research. And the work is motivated by applications that arise in the field of spintronics. It's an emergent field of microelectronics in which one wishes to take advantage of both the charge and the spin degree of freedom of the electron for information technologies. I think this works. Okay, so magnetic skyrmions, what are they? I will make it precise which kind of magnetic skyrmions I'm going to be talking about. Actually, they are not the kind of they appear not in the kind of materials that Ben was talking about. I'm going to be talking about skyrmions that arise in essentially atomically thin metallic ferromagnetic layers. So as such, these materials are not chiral. Okay, and I will discuss it in a second. What causes the emergence of magnetic skyrmions? But what are they from the point of view of the experiment? They are just tiny whirls of spins. So in a background of a perpendicularly magnetized ferromagnetic field, they are just magnetic moments that are rotating in the opposite direction in some sort of localized fashion. And these kinds of skyrmions in these materials were first observed in the work of Roming and others in 2015. And since they are particles, so these are the observations of this magnetic cartoon and an observation of these magnetic skyrmions under strong magnetic, very strong magnetic fields. You see here about 3 Tesla, and at very low temperatures. But very quickly it was recognized that these are, and the scale, I should also say, is just a few nanometers. And so very quickly they were recognized as potential information carriers that are very, very dense and can be manipulated by very low power. And so a quest for magnetic skyrmions suitable for applications started, and you can see this through the explosion in the number of publications of magnetic skyrmions in these systems. As of today, since 2000, in the last 10 years, we have about over 2,000 publications on the subject. And so, okay, so one of the important situations where people would like to observe skyrmions is materials under more normal conditions. And so there was a work where skyrmions were observed in materials at room temperature and fairly low magnetic fields. And then this was followed by work where zero field magnetic skyrmions were observed at room temperature in sort of under confinement in magnetic nanodots, and using different types of materials. One could produce, again, zero magnetic field stable, room temperature stable Skyrmions in 2018. And these, there is a range of materials that quickly emerge that exhibit magnetic Skyrmions, and they also exhibit very different scales. So here we are talking about nanoscale Skyrmions, while in these room temperature stable Skyrmions, the characteristic length scale of this configuration is more on the order of 100 nanometer, but in fact there are other materials where the Skyrmions are essentially a more bubble-like solution, bubble-like configurations with sizes exceeding microns. Okay, and there exist also Skyrmions as single point-like objects have been already observed for a while, but new observations produce some more complicated configurations with some internal structure which might be interpreted as higher topological degree Skyrmions. Okay, so this is sort of the experimental picture, but where is this terminology coming from? So why Skyrmions? Okay, here we need to get our language straight a bit. And so what are Skyrmions? Skyrmions are an example of topological solitons. Okay, so as such they are particle-like solutions of some nonlinear PDEs with non-trivial topology. Okay, and as such, in order to start talking about really making sense of what we mean by Skyrmions, we need to say, okay, what model are we talking about? Which are the unknowns? Which are the equations that we have to solve? Which are these equations, nonlinear PDEs? In which spatial domain? And which topology is associated with them? Okay, and once we specify this model, we need to know, well, okay, so we start looking for the solutions, and we need to know whether they exist, are they unique, how many of them there are, what do they look like, are they stable in particular? Okay, so these are not trivial questions, but in the case of magnetic Skyrmions and ultra-thin films, there is actually a very well-defined continuum framework in which these questions can be answered, and this is the modeling framework of micromagnetics. So in this particular case, the unknown is a three-dimensional vector of unit length. Okay, and one can see, and the domain in which this vector lives is the whole plane, which is compactified by assuming that the magnetization is constant perpendicular to the film plane, which I'm going to always take to be direct pointing down for definiteness. And so it's a compactified plane, and so the maps, therefore the variable in question are maps from a compactified plane to S2, and they're expected to be smooth, so no singularities will be expected to arise here. And in this case, a topology can be characterized by the Brouwer degree of such maps, okay, which has a nice integral representation in the form of this integral, which just measures how many times the image of the map wraps around the sphere, counting the orientation. Okay, so the equations arise from a suitable micromagnetic energy functional defined on these maps, and in particular, stability is equivalent to the local minimality of the micromagnetic energy. Okay, the original, the origin of the notion of Skyrmions goes back to the work of Tony Skyrm in the context of nuclear physics, and so as topologically non-trivial solitons in nonlinear field theories, and these problems started to receive considerable mathematical attention in the 80s, and with the work of a number of people working in the subject. And for our purposes, I will illustrate this with an example which gives rise to what's called baby Skyrmions. Okay, and in this example, the variable is as before, maps from plane to sphere, and they are solutions of the Euler-Lagrange equation associated with this energy functional. Okay, so here n is just a constant vector. Okay, and so this functional consists of the Dirichlet energy, some sort of energy that forces the vector u to align with n. Okay, and what is called a Skyrm term. Okay. And in the absence of this Skyrm term, it's easy to see that there can be no critical points for this energy. And I will illustrate it in a second using the Dirac-Pakhajaev argument. So, and essentially, this in two space dimensions here, the Dirichlet energy is scale invariant. So if we take a configuration and shrink it, the energy doesn't change. But for any configuration that goes to n at infinity, would of course make this smaller, this term smaller if we shrink the configuration. So what this term does, as Bernard already said, is some sort of fourth order derivative, fourth order gradient to the fourth power type term. Okay, this term becomes very large when things are compressed, and so there is a kind of a balance between the two terms here. Okay, and as a consequence, and it is known for this problem that there exist energy minimizers in the non-trivial topological degree class for degrees plus or minus 1. Okay, now in ferromagnetic magnetic films, the existence of magnetic Skyrmions is instead caused by another type of interaction, which is a type of interaction, chiral interaction, which is called the Zelashinsky-Marie interaction. Okay, and it is a sort of a type of an exchange interaction between neighboring spins, which is called an antisymmetric exchange, where ferromagnetism is caused by the presence of the basic symmetric exchange, which is, you know, and if you look at the Heisenberg models of spins, is just interaction of nearest neighbors, which tend to align the spins, and so this energy causes all the spins in the sample to be pointing in the same direction. But in 1957, Zelashinsky used symmetry arguments in the context of weak ferromagnetism in iron oxides. He proposed another term for materials that are lacking central symmetry. And the term is of this form, and instead of the scalar product of two spins at adjacent lattice sites, you have a cross product, and this is multiplied by what is called the Zelashinsky vector. Okay, and this kind of interaction was then derived from first principles by Muria as an interaction mediated between two magnetic two spins mediated by a high spin orbit non-magnetic atom, some sort of impurity. And in this situation, so if you look at two spins and an impurity, it turns out that the Zelashinsky vector is a vector that is pointing normally to the triangle formed by the three the constitutives of this interaction. Okay, and the same effect so this effect was pointed out to be significant, actually unusually strong by Fert and Levy. Okay, in the context of spin glasses, and then it was observed that actually if one has a layer of non-magnetic high spin orbit coupling metal like platinum on top of a ferromagnetic layer like cobalt, then the non-magnetic metal itself plays a role of an impurity mediating the Zelashinsky-Marie interaction, and therefore it produces the Zelashinsky vector, which is in the plane of the interface and causes the spins to rotate in the sort of what is called a Niel fashion. Okay, so and so a competition of the direct and indirect exchange produces what is called spin spirals or helices, and under the Zaleshinsky-Barry interaction, they are as I already said, of Niel type when the rotation goes like this. This is in contrast with spin spirals that occur due to competition of exchange interaction and stray field, where the rotation is instead of block type, which is sort of screw-like. Okay, and these configurations again are observed experimentally, but in experiments there are other interactions that come into play, in particular perpendicular magnetic anisotropy, which replaces these sort of spin spiral states with chiral domain walls. So, for example, here we are looking at the image of sort of magnetic strips where the color corresponds to the in-plane component of the magnetization. So, for example, going from here to here, the magnetization goes from up to down while looking up. Okay, so from out of plane, out of the board, down to the board, while rotating in a Niel form with in the up direction. But you also see walls which look like this, where there are actually a full 360-degree rotation of the magnetization. And these are actually examples of so-called topological defect, because the two states on both sides of the wall are indistinguishable physically from one another. The only difference is that there is a full rotation of the magnetization vector. And so this is how the non-trivial topological configurations emerge, and then imagine that you take this 360-degree wall and wrap it around a point, make it a radial configuration, and you obtain a configuration which is a magnetic skyrmion. Depending on how you rotate, you could have a Niel type skyrmion or a block type skyrmion. These pictures we already saw in Bern's talk. These skyrmions were found experimentally and numerically, and experimentally they are shown to be susceptible to the application of currents. They can be moved by currents, and so therefore they are candidates for the next generation spintronic devices, such as this skyrmion racetrack. Okay. And so we would like to understand these kinds of states in a mathematical term. So, as I said, the starting point of analysis is the micromagnetics of ultrathin films. So, again, we are talking about atomically thin extended ferromagnetic films with perpendicular magnetic anisotropy and interfacial Zaleshinsky-Barry interaction. So, the state variable here is a map from R2 to S2. And I'm going to use always this notation where M parallel is the component of M parallel to the normal, to the film, and M perpendicular is the normal direction is the easy axis direction. So M wants to be either up or down. Okay, so the component parallel to the easy axis is M parallel, and the one perpendicular to the easy axis is M perpendicular. Okay. So, and the energy consists of a number of terms. So, okay, so let's see what they are. So there's an exchange interaction, which is, the continuum version of this Heisenberg direct exchange, which is just a gradient squared that penalizes the variations of magnetization in space. There's an anisotropy, the energy which penalizes the in-plane component of the magnetization. There is a Zeeman energy term which penalizes the deviation of the magnetization from the down state. But in the rest of the talk here, I will set this term actually to 0 because I don't have too much time. And let me just say that this implies that this rules out the solution that Bern was talking about. So this would not be possible. Okay, and here the interfacial DMI term, which has this form in a continuum approximation. There are some dimensionless parameters which measure the relative strengths of these interactions. Okay, and some scales. Yes. And okay, I didn't mention the last term here. I forgot to mention that this is a tricky term. This is what is called a stray field energy, and it arises because the spins are actually, electrons have tiny magnetic moments, which when the system is in a ferromagnetic state produces a magnetic field, and this magnetic field causes an interaction between spins far apart, so long-range interaction. In the context of thin film materials, it is possible to show using the techniques of gamma expansions that to the leading order in the film thickness, the stray field energy has the following form. This is due to essentially the interaction of two types of charges. So the stray field interaction can be thought of as Coulombic interaction of charges, which are the distributional divergence of the magnetization, and this charge density consists of the so-called volume charges that are due to the in-plane magnetization component inside the film, but also the surface charges due to the jump discontinuity in the magnetization between sample and vacuum. And so to the leading order, the stray field energy can be approximated simply by an effective shape anisotropy term, which is essentially an energy of a parallel plate capacitor associated with this picture. And then the corrections to that are given by these non-local dipolar terms, which is the h minus 1/2 norm squared homogeneous of the divergence of the in-plane component with a positive sign, so it's a positive term, and then minus the h 1/2 norm squared of the out-of-plane component. And okay, so this model, as you already saw in Bernd's slide, it produces a great variety of solutions, and starting from the skyrmion itself, and these kind of solutions were first observed starting with numerically in 1989 by Bogdanov and collaborators. And okay, so but in addition to these kind of solutions, there is a whole zoo of solutions, and the question is, what can we actually understand from the mathematical point of view about these solutions? Okay, so to get an idea what one can do, I'm going to focus first on the minimal model. So as I told you, that the stray field interaction to the leading order simply changes the constant in front of the anisotropy term, and so after integration by parts, the energy has this particularly simple form where Q is bigger than 1, so this is a positive coefficient. Okay, and one wants to try to understand the existence of local energy minimizers for this, non-trivial local energy minimizers for this energy. Okay, and okay, the first observation is easy to see that if the DMI strength here is sufficiently weak, okay, then the global ground state of the global energy minimizer of this energy is m equals constant up or down, corresponding to perpendicularly magnetized film. And this is easy to see, so just okay, apply Cauchy-Schwarz and then complete the square here, Young, and clearly the energy is bigger than 0, which is the energy of plus or minus z. This is 0, okay, strictly bigger than 0 unless m is constant and equal to plus or minus z. So all the global energy minimizers in this problem are trivial. So we need to introduce some constraints in order to look for some non-trivial minimizers, and one such possible constraint is to specify the value of topological degree of a map. And in this variational context, again, due to the work of Brisis and Coron, this is an appropriate definition of the degree. Okay, and okay, if for kappa sufficiently small, we have that the infimum of the energy over the non-trivial, topologically non-trivial configurations where n is not 0 is strictly positive. And this can be seen from the well-known topological lower bound that Bernd already mentioned, which is just a simple consequence of an algebraic vector identity. So one could try to look for energy minimizers for this energy. For this energy, okay, specifying the degree of the map, okay, and okay, so as a warm-up, one could set all the coefficients of the model other than the exchange length to zero, term to zero, and in that case, we are left with Dirichlet energy, and this is a well-known, well-studied problem of harmonic maps, whose minimizers were first identified in Bilavin and Polyakov, and they are, after stereographic projections, they are all rational functions of Z or their complex conjugates, and the minimum the minimal value of the energy saturates the topological lower bound. And they are also the only critical points of this energy, as was shown by Lemaire, and there's huge literature on the subject, of course. And specifically, all degree 1 energy minimizers are rotations, translations, and dilations of the canonical Bilavin-Polyakov profile, which is what we associate with the Niels-Skyrmion. Okay, so one could try to go on and minimize the energy, our energy in this class. Okay, so what we do is we are considering the admissible class of functions whose gradient is now 2 with topological degree 1, and we added additional assumption that M converges in some average sense to minus Z at infinity, which is not really a restriction. And under these assumptions, we have a theorem that for any Q bigger than 1 and kappa real and smaller than this explicit threshold, there exists a minimizer in this class. Okay, and this is a nearly optimal result because there are actually no minimizers in the case kappa equals 0, and it is known also that for kappa sufficiently large, bigger than this threshold, the minimizers, the infimum of the energy is minus infinity because the system wants to form helixes instead. Okay, so to get an idea how this works, okay, well, and why we actually need the DMI here, well, let's first consider the case of kappa equals 0. Okay, in this case, the energy is of this form, and let's suppose we have a minimizer. Okay, we call it M0. And then we can just dilate this minimizer and use it as a test function, and then the energy, since the exchange energy is scale invariant, this term will, the exchange energy will be unchanged, but the energy, the anisotropy energy will be multiplied by the factor rho squared, and therefore choosing rho very small, so shrinking the profile, always lowers the energy. Okay, so this is the essence of the Derek-Pakhajaev argument for non-existence of critical points for this energy. In contrast, if we take a configuration in which also has, for the full energy, which has this integral that is positive, then this picture is modified like this. There is actually a negative slope at rho equals 0, and therefore, choosing rho appropriately, we can have something which has energy energy minimum among all the dilations, so to say. And okay, and then choosing as M0 as a suitable truncated Bilavin-Polyakov profile, we can ensure that the minimum of this energy goes below the topological lower bound for degree 1 configurations, and this fact can be used to prove existence of minimizers, and this is following the work of Melker from almost 10 years ago, and essentially relying on the arguments of Brisis and Coron. Okay, what about the full model? Coming back to the full model with the dipolar terms, well, this program unfortunately doesn't really work, and the reason for that is that actually there is now a competition between the compact magnetic skyrmions, which we were investigating before, and the so-called skyrmionic bubble. So such a configuration can be shown, which has its degree 1, it's a Bloch rotation, Bloch domain wall connecting the two states, plus and minus 1 in the normal direction. Okay, this can be shown to have the surface charge energy, this term, which diverges as minus delta rho, r log r, while all the other terms in this energy behave as R. And so this by choosing R sufficiently large, we can make this arbitrarily large negative. So the energy is no longer bounded from below. So some additional constraints need to be introduced, and this is what we did in this case. We introduced an additional constraint that the Dirichlet energy is not more than 16 pi, which is twice the topological lower bound for the single Skyrmion of degree 1. And this is essentially to rule out the splitting of Skyrmions into two non-trivial components in the concentration compactness arguments to prove existence. So if that happens, then the energy, the exchange energy has to be at least 16 pi. And this allows us to prove existence of magnetic Skyrmions in this parametric range. Again, not optimal, but hopefully not too far from the optimal at least.
Is this for which degrees is this?
It's degree plus 1.
Is this for degree plus 1?
Only degree plus 1. Yeah.
Which is what I put -1.
Yeah. I like plus for Skyrmion, so that's why we chose this conventions. Yeah. Okay, but not only that, we can actually completely characterize so we have existence, but very little is actually known about these solutions. What are their shapes? What do they look like? Nevertheless, in the particular special case, when both of these parameters kappa and delta are small, which corresponds to what is called conformal limit, we can prove, we can give a precise characterization of the minimizers. And let's take it for our simplified local model first. So let's take, so we have the following theorem. So let's take kappa, sequence of kappas going to 0 and the associated minimizers of E kappa, which always exist for small enough kappa, okay? And then there exist centers, radii, and radii such that the difference between the minimizer and the Niel-Belain-Polikov profile suitably translated by this center and dilated by this radius goes to 0 in H1 homogeneous norm. Okay, and the radii have an explicit asymptotic behavior as kappa goes to 0. Now, since H1 half homogeneous norm is actually dilation invariant, this also means that the suitable dilation of the minimizer converges to the canonical Niel profile, suitable dilation and translation of the minimizer. So the minimizers converge in shape to the expected Niel profile. And this is a consequence of the rigidity estimates that Melanie was talking about for degree 1 Skyrmions, where we proved in the joint work with Anne and Teresa that the Dirichlet distance squared between an optimal Belain-Polikov profile that minimizes this distance to a given admissible configuration. M is controlled up to a universal constant by the excess of the topological lower bound. Okay, now instead of giving you a statement, what happens in a full model, I just give you a little drawing, and this is just the leading order prediction of the asymptotic theory for the behavior of the minimizers in the conformal limit. In a model that also contains a stray field effect. And so for sufficiently small stray field contributions, so for sufficiently thin film, so to say, the Skyrmion retains its Niel character, but then at some critical value of the ratio of the DMI to thickness, there is a transition to mixed Niel-Bloch profiles, and at 0 DMI we have a purely Bloch existence of purely Bloch Skyrmion that is actually stabilized only by the presence of these non-local stray fields, even when kappa is equal to 0, and this is confirmed by direct numerical simulations. Okay, I have not so much time, so I'll try to be quick. So okay, so from here, what about bounded domains? So okay, so the question is, how do we define a suitable topology in a bounded domain? And okay, so a naive thing to do is just to say, take our our simplest model and just reduce the domain of the problem to a bounded domain, but there's no longer a notion of topology here anymore. We cannot define a degree, and in fact, it is well known in this case that trying to minimize energy often produces configurations that attempt to escape through the boundary. Okay, this could be rectified if we replace free boundary conditions by Dirichlet boundary conditions, where we pin the magnetization to be pointing down at the boundary of our sample. This restores the topological degree, which is now given by this expression, just by extending magnetization by constant to infinity and reducing to outside the domain and reducing to the case that we already studied. Okay, so now our admissible class looks like this, and we have again an energy which again we integrated by parts here. Okay, and so the question is, okay, so what can we say about existence of minimizers in this case? And here we can also specify the degree to be a given number d integer. Okay. Okay. Well, that's a bit of a cheating, because I just try to put by hand the boundary conditions that work for our purposes, but in fact it's not really the case, because I don't have time to explain to you this, but in fact a full treatment of micromagnetic energy, including the stray field contributions, results in some singular behavior of the magnetic field near the edges of the sample, which is essentially the effect of fringe fields in parallel plate capacitor in the simplest case. And so these actually produce additional penalties, which is first identified in another context by Kohn and Slastikov, and force the magnetization to align with the easy axis also at the edges. And this has been shown by us in our work with Giovanni and Valeri in a recent paper via suitable gamma limit. Okay, so what happens with Skyrmions under confinement? Okay, so we are now considering minimization of this energy in respect to this admissible class. And it's an easier problem because now we are on a bounded domain, so there's the only sort of loss of compactness we could have is by things concentrating and okay, adapting the same arguments. We can prove that there exist minimizers with degree 1 for every kappa sufficiently small and give a fixed Q. Okay, and we can also consider conformal limit again, which can be completely characterized using shrinking Niel-Bilan Polyakov profiles of radius of order kappa, whose center has to take a certain position in the domain that can be calculated explicitly. In particular, in a disk, a minimizer goes to the center. Okay, so what about multiple Skyrmions then? Okay, so my last several slides will discuss our recent work, which was just accepted, on existence of higher degree Skyrmions. Everything I told you about are minimizers with degree 1. Incidentally, even if my rigidity estimates are valid for degree -1 configurations, I could try to turn the crank and try to prove existence of anti-Skyrmions. Actually, we don't have a proof of that. And in fact, I suspect that there are no anti-Skyrmion minimizers for this energy. Okay? But what about higher degree minimizers? Okay, so degree larger than 1, 2, etc. Okay. All right. Well, existence of minimizers would be tackled by the direct method of calculus of variation, and okay, lower semi-continuity of this function is straightforward. Okay, it's just that we have two norms here, and a weak strong argument applies. Okay, and also good coercivity for kappa, which is not too big, because again we can complete the square, and explicitly easy to see that the energy is bounded below by a multiple of the Dirichlet energy with a constant slightly less than 1. Okay, for kappa sufficiently small. So the only issue is, can we make sure that the degree of the minimizers is preserved in the limit of a minimizing sequence? This point is not at all straightforward because minimizing sequences can concentrate and the Dirichlet energy density can concentrate on a delta, on Dirac delta. Okay, so but this was already realized in the work in the 80s by Brizis and Coron, and they came up with this very beautiful trick that allows to prove existence show that under certain conditions the degree of the minimizing sequences are preserved. And this is just again the same algebraic trick we used for the topological lower bound, which says that the Dirichlet energy plus minus 8 pi times the degree is equal to an L2 norm squared of something. Okay, and therefore weak convergence in H1 implies L2 convergence, weak convergence here, and as this is a norm, this is lower semi-continuous. So, okay, so if we take a minimizing sequence that converges to some limit, together with the derivatives, then we have the following inequalities. So the energy, so due to this lower semi-continuity, the sum of the energy plus minus the degree is less or equal than the limit of the energy plus minus the degree on the sequence, but on the sequence the degree is d, and this is just the infimum of the energy on this class. Okay, so for kappa sufficiently small, now on the other hand, from this estimate here is clear that for kappa sufficiently small, the energy is always non-negative. Okay, and is zero for zero if and only if m is 0. Okay, so the energy is, on one hand, for every limit configuration, the energy, non-trivial limit configuration, the energy is supposed to be positive, and using an ansatz of well-separated, regularized Belaïen-Polyakov profiles, non-interacting Belaïen-Polyakov profiles, it is possible to show that the energy, the infimum of this energy is actually strictly less than 8 pi d. Okay, d times the topological lower bound. So if we take a negative sign in this inequality, it's immediately clear. So this is estimated by 0. Take the negative sign, and so this degree d here cancels. So very quickly so this is less than 8 pi d. This is 8 pi d. So this is 0. So quickly we get that n is bigger than 0. So n has to be greater or equal to 1 because it's an integer. Okay, now taking the plus sign, we need to do a little more work, and so we estimate the energy as before, and then also use the topological lower bound. So the energy of the limit can be estimated now by this guy, and here we estimate the right hand side by 16 pi d, 8 pi d plus another 8 pi d, and this again implies that n has to be less or equal to d, and you can see from here that we are done already for d equals 1, because then n equals what we want it to be. But in where d is bigger than 1, this opens a possibility that the degree of the limit may jump down. Okay, so how would one want to? How could one prove existence of prove that the degree doesn't actually jump? Well, we can prove that provided we have some sort of strict subadditivity of the energy with respect to degree. So every time I add a degree, my energy, infimum energy, should actually grow by strictly less than 8 pi. If that is the case, then again, using these inequalities that I showed you before, so just turning the crank, arguing by contradiction, we arrive at a contradiction. The infimum of energy over the degree n less than d should minus 8 pi, and the limit degree should be less or equal than corresponding infima by degree d. But then applying n minus d times this inequality, you get a strict inequality with respect to infimum with respect to degree n, going down in degree, plus something which is 0, and so this is a contradiction. So we need to prove existence of minimizers, we need to show that this is satisfied. And it turns out that this is a non-trivial fact because, so essentially we want to insert in a configuration, say a minimizer with degree d minus 1, we want to insert a small Beeline Polakov profile to raise the degree to d, okay, while raising the energy by something slightly less than 8 pi, okay, and this turns out to be, appears to be generally impossible. But a sufficient condition for that, so it requires, so we can surely do that if m is, say, flat somewhere, if it's identically equal to constant, okay, somewhere. Say, if I have a place where m is pointing up, I can insert the line Polakov profile pointing down and gain. But for a configuration where the gradient is never 0, this is not obvious. And so we have, however, we have this result. If we can find a ball in a domain such that this sort of energy density is sufficiently small at the order of kappa squared, it is always possible to show that the energy, there is such a place where this is of order kappa squared, but we want it to be of order kappa squared with small coefficient, small universal coefficient. Then our strict subadditivity assumption is valid, and this would give existence of minimizers. So this last theorem provides conditions under which we can prove that this lemma, the assumptions of the previous lemma are satisfied, and these yield existence of minimizers with a given degree d. So given a natural number d, q and kappa, provided that kappa squared over q minus 1 is less or equal to this quantity. Remember, for existence we had something like 1 over root 2 here. Okay, so this is a stricter inequality. Then there exists a constant C0 such that if omega is a domain with Lipschitz boundary with sufficiently large area in terms of d, and then there exists a minimizer with degree d. Okay, so this is what we were able to prove. This is the first result on existence of higher degree minimizers under confinement. And okay, so just a few remarks on this theorem. We actually don't know anything about the shape of these minimizers. In particular, we don't know how they behave as kappa goes to 0. Do they look like a bunch of well-separated single-degree Skyrmions, or is it some kind of cluster of Skyrmions? We don't know that. We can also prove an analogous result for existence even in the case of q equals 1, so no anisotropy term, just exchange and TMI, but only in elongated domains. And we don't know whether or not there exists a higher degree minimizer, for example, on a disk, while we know that there is always a degree 1 minimizer on a disk, and for small enough kappa, it has to be concentrated near the origin, okay? And then, of course, these assumptions are by no means sharp. You might think that, okay, this assumption looks good because I have to have a certain area per Skyrmion. Okay, d. So if I increase d, then the area that I should have in my domain should be proportional to d. Actually, it's not quite the case because this condition actually requires that kappa squared is like 1 over d. And so when we plug it in here, then in fact we need omega to be bigger than d squared. And that, for example, wouldn't rule out the possibility that our minimizers line up as Skyrmions that are lining up over near the boundary of our domain instead of going in the interior. Okay, so we don't know what to expect. And finally, these types of arguments, of course, cannot say anything about unbounded domains because there we really need to understand what kind of interactions are there. Are there some sort of attractive interactions among well-separated Skyrmions or not? And so this is currently working for this. Sorry I went over time. Thank you very much for your attention.
I wonder to what extent your analysis takes into account the intuition that I would get from Philip and Nikolai's picture, which is a bunch of Skyrmions in a bag.
Yeah.
And the Skyrmions, because you can't individually, for nuclear Skyrmions, you can prove there's an attractive configuration by
I should say that this bag, it kind of works as our bounded domain.
Yes,
it's sort of like it provides confinement.
Right.
Yeah.
I mean, that's exactly how I would interpret it, because you cannot rotate individual skyrmions to make them attractive. That's not an option, because the theory doesn't have that symmetry. And the standard configuration is repulsive, so they like to be away from each other.
Well, okay,
And
so,
then the skyrmionium, that's one big magnetic wall.
Okay,
That's got negative energy, and so that provides the tension to pull them.
All right, so the point not to forget is that we're trying to look for global minimizers. So skyrmionium would not be a global minimizer.
But no, I mean, but the bag is skyrmionium.
Yeah, okay, so even that probably, for kappa small, that would not be a global energy minimizer. It would cost too much energy to have this big bag.
But it's got, I think it has negative, and I think that provides, that captures the skyrmions.
But it's outside the regime that we're studying.
I think without the bag, the skyrmions would fly apart.
Yeah.
And so this big loop of skyrmionium actually holds them together.
Sure. But okay, so in the problem with, okay, so this bag is really, you can instead put a boundary and it works like a bag. The problem is not that. The problem, so they are held together. The problem is that if there are too many of them, some of them may just want to shrink to nothing. And so here, contrary to Ginzburg-Landau vortices, which is, by the way, it's some kind of a new variant of the variational framework for the kind of questions that were studied by Brisis Betwell for complex Ginzburg-Landau for superconductivity. In superconductivity, vortices cannot disappear. Okay, you have to pay infinite energy. But here, a Bilavin-Polyakov profile can shrink and you just pay constant. And so the energy alone is not sufficient. So when you have one skyrmion, then you kind of can work at small deviations from the energy of one skyrmion. But once you have two skyrmions, okay, you can just shrink one, you gain enormously. And so,
okay, so that's an additional.
That's a real complication.
God. I'm going to postpone further discussion to the already shorter coffee break. I am sorry to all the people who want to ask questions. Let's thank the speaker.
Thank you for your patience.